Right there, ladies and gentlemen, let's go ahead and start. This is a more formal version, of course, than the quick notes I gave you in class. So if you want it more formal so you can take it on a test, here you go. I'll try to go as quick as I possibly can. So we're talking dilations, the weird cousin to the transformations that we saw before. So even though this is going to have similar parts to like a rotation, reflection, a translation, like the rule and the structure and all that, it behaves very differently. You saw that in class, and we'll see it out here. So you have this essential question, like how do you perform and identify a dilation transform on and off the coordinate plane by using both the structure and the rule? It's basically the same question I asked you about the other three things, rotations, reflections, translations. But now we're looking at dilations. Let's knock out some vocabulary first. This is a good time to remind you that you need to put questions right here because I'm not going to let you use these notes on the next test unless these are properly formatted. I kind of let it slide the first one go around, but this time around, if you don't have the stuff there, I'm going to ask you to put those notes away. All right? So we'll talk dilation. So a dilation is nothing more than an example of a non-rigid transformation. So transformation, of course, means that it's just moving an object. So a rotation, reflection, translation, those are all types of transformations because it's changing the where it is in a way. Those are rigid. This one's non-rigid because a non-rigid transformation, a non-rigid transform, changes the configuration of the object while it's actually transforming. Okay, that word's transforming. So unlike translations, reflections, rotations, where they're going to keep the exact same shape even though it's moving it, dilations won't. Like they're going to actually change it. You saw that in class. It's going to make it bigger or smaller, which is what dilations actually do. So we have some important parts we need to kind of knock out. Center dilation is, let's actually change that. It's a point at which the dilation starts. So someone pointed out that it's a lot like a center of rotation, where that's kind of where the rotation all takes place. It all revolves around that point. Dilations are similar in that way. The center dilation is not going to move during a dilation. It's not part of the moving parts. So it's very similar to a center of rotation, but it's really where the dilation begins, where it emanates. The K factor is the scaling factor, which is the same thing as a multiplication factor. And don't let that fool you. Like multiplication could also be division, which is how the thing actually gets smaller. Another way to say that is how many times bigger or smaller an object actually gets. So if you know the K factor is 2, it's twice as big. If the K factor is 1/4, it's 25% as big. If the K factor is 8, it's 8 times as big. And we'll show you guys how that kind of plays out. Lines of dilation, these are kind of weird, but they start at the center of dilation, and it's where the image travels. Sorry for my bad handwriting. Let me fix this word. That word is points. There we go. A little better. Okay. So these are the main vocabulary terms that we need to kind of think about when we're talking about dilations. But the best way to kind of answer the question is to jump right into a couple examples and kind of see how this all changes, or how this is going to change an object, I should say more precisely. So let's say I want to perform this dilation of an object, and I'm going to give you the algebraic rule. And so let's say the algebraic rule is that every point x comma y on my object will travel to 3x, 3y. So this is important for a couple different reasons. One, of course, this is just a point rule, but more importantly, these 3's are going to be the k factor, which means every point in this object is going to be 3 times bigger than it was in its original. Now that means points, that also means side lengths, because points, of course, make sides. So let's say the thing I'm trying to transform on this grid has some coordinates, and I won't go crazy here. I'll just pick 3, and I'm not going to even grid it in. I'm just going to kind of take a guess of where they'd be. So let's say this is at -1, 2. Let's say B is at 4, 1, and let's say C. Let's do a negative. Actually, let's do negative right here. So let's say C is at 0, -3. Okay, so I have this nice little triangle here. Now the algebraic rule, 3x, 3y, assumes the center dilation is at the origin. Otherwise, you're going to have to do a little bit more thinking on that. But using this rule, I can actually feed a, b, and c into this. So a was -1, 2. By the rule, I multiply both of those by 3, so it gets -3, 6. B starts out at 4, 1, but through this transformation, I'll end up at 12, 3. And then C was at 0, -3, and then that's going to end up at 0, of course, because times 3 is 0, and then -9. So when I graph these out, and I'll graph them in green, let's see, B is going to be, B is going to be at 12, 3, so probably about right there, so that's B prime, 12, 3. This one's easy. This will be 0, -9. So out there. And these are all just guesses, you know. I'm not entirely sure precise where these will go, but you get the point. So -3, 6. So there-ish. Okay. So this new object, the one that's been dilated, in this case bigger, what we can say is 2 times bigger than the original object. I'm sorry, 3 times bigger, because K factor is 3. But we can also notice some other things structurally that have to take place. One notable thing is lines of dilation. So if that's my center of dilation right there, and I take this and connect it through B and then continue on to B prime, and of course A and A prime, C and C prime, note that all 3 of those lines of dilation come right back to the center. If you're really clever and looking really carefully, you'll also notice that these are parallel. But again, since we're kind of just stretching the object out, this should make sense. This is no different than resizing an image like in like Microsoft Word or like a Google image. So for example, let's say I have this like star right here. If I take this and only stretch it one way, oh, one little guy. Okay, so only stretch it one way. That's different than saying only stretching it like side to side. So this is not a great example here because I thought I could move it just independently, but I can't. But I can show you here. So what I kind of mean is if I take this object, star, here we go. On there. Okay, well. Okay, so let's take a quick detour. I'm not quite sure why that wasn't working before. Here we have Stewie Griffin. So here's what I mean kind of by the stretching. So if I would take Stewie Griffin and stretch and resize him, and I'm going to resize top, like up and down and vertically and side to side at the same time. Although Stewie would get bigger and smaller, he totally seems like in proportion. But if I were to stretch him just this way, just horizontally, and make him no taller, like he'd get really, really wide and out of whack. Same if I would take Stewie and just stretch him this way. Same kind of idea. He'd get really tall, but he wouldn't be proportioned well because, well, I'm only stretching him vertically. And so that's kind of what you're seeing here, these lines of dilation. The reason that these end up being parallel is because like these points like A, B, and C have to travel along the blue lines at the same rate. In this case, the rate is times 3, which is why they end up kind of sizing to this nice bigger version that's not out of sync or not an aspect ratio. So that's something to kind of keep your mind as you think about these dilations. This is why those lines have to be parallel on the lines through the lines of dilation. Okay. The last thing I want to mention, and just kind of we'll wrap it up, is that there is a generic rule for this. Of course, on the grid, it makes sense to use the algebraic rule, but we know that's not necessarily good enough. So we can use like a D for dilation. So the two things you have to know by dilation, of course, will be the center of dilation, and then also the K factor. And then you can always take then your pre-image to your image. Okay. So this is all I kind of want to wrap up and say about the non-rigid dilation. So you have this rule that exists, you have this algebraic rule that exists, but in the end, the big takeaway here is that this is a non-rigid shape. The main reason for the non-rigidity is actually this right here. The multiplication, that's the first time we've seen that in a rule, and it's had a kind of a dramatic effect. The K factor is the reason why it's non-rigid. Okay? Which, again, this should make some sense. Let me explain what I mean. If you say, let me scroll down here. So if you kind of think about why multiplication is actually making this non-rigid, here's an example of what I mean. Let's say you take like Oprah, and you take her bank account, and let's say there is $2 million in her bank account right now, which is probably low because she's like Oprah, right? And then let's say you take my bank account, and let's say I have 20 bucks in there, right? Which is probably pretty accurate. All right. If I were to take and add 5 to each one, okay, it would gain the same amount. So of course this would be at $2,005, and mine would be at $25, but we gain the same exact amount. If you were to take that away and say, well, Oprah, I'm going to double the amount of money that you have, and Mr. Collins, I'm going to double the amount of money you have, the gain here would be $2 million. And while my gain would be $20. So even though we're doing the exact same operation to both, the gains are completely different because we had a lot more to start with Oprah than he did with me, which is why ultimately the multiplication factor is what's throwing everything off and making it bigger. Because the bigger the point you had to work with, like 4 as opposed to 1, it changes the stretching horizontally and vertically, which is why 4 went all the way to 12, a gain of 8, and why 1 only went to 3, a gain of 2. That's what multiplication does. So that's the reason why it's non-rigid. So hopefully that can help answer that question a little bit. That's all I have for dilations, guys. It's pretty short and to the point. Again, please don't forget to format these well. And so there should be questions here in these empty boxes. And of course, since these are going to be good notes you probably going to want to use, don't forget to do a summary. And again, if you're posting these, you get to get those points back on the test. So please do it. And that's all I got for you guys. Thank you.